apart. It's not stable. And so you extrapolate, for instance, the derivatives of the elastic constants with effective temperature up to Mantle temperatures. You end up getting just one factor that's affecting the temperature derivatives of the elastic constants. What I was finding is, in fact, there was an effect on the elastic constants as a direct result of the disordering. And because the disordering is a function of temperature, there is an effect, a secondary effect on the elastic constants as a function of temperature as you have a change in the degree of disordering. And so one of the predictions then that I've managed to make, and this looks great on my computer. You can't see where I've covered things up. But you can make these predictions where, in fact, the impedance contrast between, for instance, the wodslite and ringwoodite as you go across the 520 starts to decrease as you go to higher temperatures. And it decreases less than you would otherwise predict based on the laboratory measurements. And so this is the consequence of the fact that that disordering is starting to kick in at those temperatures that haven't really been accessed at under experimental conditions. And to kind of feed on the theme that Kanani brought up, I started off with looking at the differences between wodslite and ringwoodite to try and figure out about my initial motivation was looking at the hydrogen. Ended up distracted looking at the disordering, and spent some time thinking. This is something where the collaborations come into play. Spent some time thinking about of how exactly we could test this and measure it. And I actually called up Jonathan Stebbins. We synthesized a ringwoodite sample at very high temperatures, or rather higher temperatures than are generally accessed, to try and look for silicon in the octahedral site, so for evidence of this cation disordering as a consequence of what we were finding. And we found diddly squat. I mean, we really didn't find anything, and it either looks like the calculations are completely off base, or that in the 5 to 10 seconds it takes to quench the sample as you're synthesizing it, when you're done, it's allowed to reorder down to kind of our detection limit was about 1% disordering. There were a couple of things. I have it out here outside this range. There are a couple of weird things in the NMR spectrum that we couldn't quite understand. And thinking about the reordering that could possibly be happening upon the quench time, there's a couple of places where silicon could be ended up in a tetrahedral site that could explain what we were seeing. But we would need, for instance, to be able to test that structure of kind of this transitory structure as the silicon's trying to find its way back to its home, that would to calculate what that NMR signal would be from that kind of intermediate form. And so the place where I'm at right now is, in fact, as kind of an armchair theorist, to try and figure out a way to calculate the NMR spectrum of the silicon-29 of silicon in a slightly disordered spot, but not quite in the octahedral site. And that's where we're at, because it turns out that my choices are very limited to be able to do that kind of calculation. And I could shell out many thousands of dollars in hopes that I will find that the code that does this will actually work, or it gets somebody else involved that can really dedicate their own resources, or willing to dedicate their own resources on something that very well could end up being a wild goose chase. So I'm going to stop there, in fact, and entertain questions. Questions? Yeah.
Okay, so someone who does both experiment and theory yourself, and self-identified end user with this great cluster access, what do you need the most from a compressed computation?
What I need is to be able to, I need what I would say the equivalent of what compressed does for non-expert users in high pressure experiments. So a couple of the beamlines at least are up to a point where you can contact the beamline scientists and say, I want to do an experiment at high pressure. And you have this back and forth communication with the beamline scientist who ultimately provides the diamond cell, the sample loading, and a tutorial on how to turn the screws, you know, to get those experiments going. And that's actually kind of where we're at. And maybe I disagree with Kanani a little bit, and that, I mean, there's definitely the problem of garbage in, garbage out, but I would expect that somebody in that situation would, for instance, understand X-ray diffraction. They understand the concept of X-ray diffraction. Provided a few tools to be able to interpret the results, and you go on your way. You have a learning curve, but you have the tools that you needed to be able to do the experiment. And ideally, the example that occurred to me earlier today was, I have an X-ray diffraction pattern of some new structure. I think I've solved the structure. You have a solved structure. It's not hard to put it into an input file and run it through an appropriate code and be able to show that it's a lower energy structure. So it's a very simple calculation to do, very simple set of calculations, broadly quite easy to interpret, something that makes a paper quite a bit stronger because you can show that, in fact, this is energetically lower energy structure. But it doesn't quite rise to that level to me of a collaboration. So, so to have kind of this, the equivalent of the beamline scientist that can help you do that is kind of what I think would bring in a lot more experimentalists to kind of have a much more realistic level of participation in ab initio calculations.
I didn't mean to. Our answers to that question are obviously different. But what I don't want is the garbage in, garbage out. Like there needs to be some guidance. And so if there is some guidance, like a beamline scientist's version of, for this facility, for some user facility, then maybe that would be okay for that, kind of structured determination. That might be just fine. But I do give credit to those who do this as their, this is their bread and butter. This is they eat, sleep, and drink the computations. I mean, there are a lot of things that need to be taken into account that may not necessarily be good for. It would be good for what running a calculation on. I think I know the structure. Is this less energy than the structure that came before it? Is the transition pressure reasonable? Okay, yeah, that might be. That's pretty easy to do, but
it's at a point right now where I think people don't do it because the barrier to getting it done is high enough that I think a lot of people don't do it. But if the tools are out there and you kind of shift that culture just a little bit further to realizing that, oh yeah, the ab initio calculations can tell us something, that's been, there's been a lot of progress in that in the last 10 years, I think, of people really accepting. Kanani and I come from a background where you distrust the ab initio calculations, and so 10 years of it being really broadly accepted. I would say broadly accepted as predictive in this community.
Right.
Yes,
okay.
in this community.
So we're how far late? We have to stop.
Right.